Welcome to next lesson in variational method and WKB approximation. In the last two classes, we have discussed the variational method and some of the applications of variational method. Now here we will discuss the WKB approximation. In the WKB approximation was formulated by three scientists, Wenzel, Kramers and Brilliant. So it is known as WKB approximation. This is an approximation method which is valid only for one-dimensional time-independent Schrodinger equation. So this can also be applied to more than one-dimensional case if the equation can be decomposed into one-dimensional equations, that is more than one-dimensional equation. For example, a three-dimensional equation in some cases can be resolved into three one-dimensional equations. So this can be applied for one-dimensional case only. So WKB approximation is applicable for one-dimensional. This WKB approximation is based on the expansion of wave function in powers of h cross. We know that in quantum mechanics h cross has a finite value, however small. And if the value of h cross is set equal to 0, we will get the classical result. So here the wave function is expanded as a term in powers of h cross raised to 0, raised to 1, raised to 2, etc. So this is also called as classical approximation, as it gives the classical result if we set the value of h cross equal to 0. Now the principle of WKB method. For that we consider the one-dimensional Schrodinger equation for a particle of energy E moving in a region of constant potential V. And there are two cases. First case is if the total energy of the electron is greater than the potential energy. This is called the classical region, because classically a particle can exist in this region. A particle can exist only if the total energy of the particle is greater than the potential energy, because kinetic energy can never be negative. So we can see that the Schrodinger wave equation in one-dimensional case is d square psi of x by dx square plus 2m by h cross square into e minus v psi is equal to 0. So that 2m by h cross square into e minus v can be taken as some k square. So it becomes k square psi of x is equal to 0. This is the famous simple harmonic equation. So the solution is psi of x is equal to a e raised to plus or minus ikx. The solution is oscillatory with a constant wavelength lambda is equal to 2 pi by k, where k is equal to 2m by h cross square into e minus v, where e is constant and v is also constant. So this is very simple. This is exactly solvable if v is a constant. Now we are considering another case in which the potential energy v of x is a slowly varying function of that position x. That is, what is meant by slowly varying is it is a constant for many wavelengths. That is, for a number of wavelengths the v of x is very slowly varying, so it can be taken as a constant for many wavelengths, that is for many lambdas. So in this case our equation for one-dimensional case d square psi by dx square plus this k square becomes 2m by h cross square into e minus v of x. V will be a function of x and k will be also a function of x. But v is slowly varying. It can be approximately taken as a constant for over many wavelengths. That is the approximation. It is a very crucial condition for the application of WKB approximation. The v of x should be slowly varying. So psi, the solution, the wave function solution is again we are approximately, it will be sinusoidal. It is also oscillatory, but with one difference, that is the amplitude A and the wavelength lambda are no longer constants. They are also slowly varying with the position x, or a and lambda are functions of x here, but in this case, if v is a constant, is an absolute constant, then a and lambda are constant. But here, as v of x is varying, this amplitude a and wavelength lambda are also slowly varying. So this was the inspiration behind the WKB method. So psi of x has two types of variation: a rapid oscillation modulated by slow variation of amplitude and wavelength. It is rapidly oscillating, it is sinusoidal, but the amplitude of that sine wave and the wavelength of that sine wave is slowly varying. Now, there are two different cases. In the first case, we have discussed the classical region, that is the region E, the energy, if the total energy is greater than the potential energy, it is called the classical region. Now, if the total energy is less than the potential energy, it is called the non-classical region. Here, the potential energy, if we take v as a constant, then we can have the solution, exact solution, psi of x is equal to a e raised to plus or minus k of x, where this k square will be 2m by h cross square into v minus e. Remember, this is v minus e. So in that case, the Schrodinger equation becomes d square psi by dx square minus 2m by h cross square into v minus e psi equal to 0. So the solution is exponential. It is exponentially increasing term is there, another exponentially decreasing term is there. In general, the solution is exponential. It is not oscillatory. This is also exactly solvable only if the potential energy is constant. Now we take the case that we are interested in. If v of x is not a constant but it is slowly varying, then our psi of x is approximately exponential, but with one difference: this a of x, that is this amplitude of that exponential function, and the power part, that is k of x, they slowly varies with x. So these are the two different regions called the classical and non-classical region. And there is one more region. If E is equal to V, what will happen? This is a more difficult case, because if total energy is equal to potential energy, this point is called a classical turning point, because according to the classical mechanics, the particle has to be trapped in the region in which E is greater than V. So if the particle reaches the point E is equal to V, it will return to the same classical region. It cannot go into the non-classical region. The particle cannot exist in non-classical region according to classical mechanics. But according to quantum mechanics, there is a definite probability of finding the particle in every region. So at this, if E is equal to V, then k will be equal to 0, because k is equal to root of 2m into E minus V. In that case, lambda is equal to 2 pi by k, it will be infinity. If lambda is equal to infinity, means the condition of slowly varying function of x, it is not satisfied, because v of x is called slowly varying only if v of x is almost a constant for a large number of wavelengths. But here the wavelength itself is extending to infinity. So v of x is no longer a constant over a single wavelength, even a single wavelength. So the condition of slowly varying function of x is not satisfied. So the WKB method can handle this difficult situation also. So that will be discussed in later when we are discussing the connection formulae. So this is the WKB approximation has three different regions. Actually, two different regions separated by a turning point. E is greater than V is called a classically allowed or classical region, and E is less than V is called a forbidden or non-classical region, and E is equal to 0 is called a classical turning point. So thank you for watching this video.